Let's explore cycle detection in graphs. Here we'll learn how to find cycles in both directed and undirected graphs. Understanding cycles is crucial in various applications, from operating systems to network analysis. What exactly is a cycle in a graph? A cycle is a path of edges and vertices where a vertex is reachable from itself. Essentially, you can start at a vertex and follow a path that leads you back to the same vertex without repeating any other vertices. Key characteristics include starting and ending at the same vertex, no other vertices are repeated, at least 3 vertices are required in simple graphs, and different definitions exist for directed versus undirected graphs. So, a simple cycle in an undirected graph can be represented as A to B to C to D to E to A. Why is cycle detection important? Cycle detection is crucial in several real-world applications. It helps in deadlock detection in operating systems, where cycles in resource allocation graphs indicate potential deadlocks. It aids in dependency resolution in package managers and build systems, which checks for circular dependencies. Cycle detection also facilitates network analysis by detecting loops in network topologies. Finally, it assists in compiler optimization by finding cycles in control flow graphs to identify loops for optimization. The concept of cycles differs slightly between directed and undirected graphs. In undirected graphs, a cycle is a path where the first and last vertices are the same, and all edges are distinct. In directed graphs, a cycle is a path where the first and last vertices are the same, and all edges follow the same direction. Note the arrows which indicate direction in directed graphs. One common approach for cycle detection is using depth-first search or DFS. The algorithm consists of traversing the graph using DFS, keeping track of visited vertices and the parent vertex, and if a visited vertex is encountered that is not the parent of the current vertex, then a cycle exists. The time complexity of this approach is big O of V plus E, where V is the number of vertices and is the number of edges. The space complexity is big O of V, where V is the number of vertices. The provided code snippet implements this algorithm in Python. For directed graphs, we can also use depth-first search or DFS, but with a slight modification. We need to keep track of the nodes in the current recursion stack. A back edge to a node in the recursion stack indicates a cycle. This is different from undirected graphs because we need to track the current path. The time complexity remains big O of V plus E, and the space complexity is big O of V. Here's the Python code demonstrating this approach. What if you need to find all cycles in a graph? Johnson's algorithm is a popular choice for finding all elementary cycles in a directed graph. The key steps of this algorithm are that it is based on depth-first search, it finds all elementary cycles, meaning no repeated vertices, it uses a blocking strategy to avoid duplicate cycles, and it systematically removes vertices to find cycles. The time complexity is big O of V plus times C plus 1, where C is the number of cycles in the graph. Another method for cycle detection in undirected graphs is the union find, also known as the disjoint set method. The steps involved are as follows. Initialize each vertex as its own set. For each edge UV, check if U and V are in the same set. If they are, a cycle exists, otherwise, union the sets containing U and V. The time complexity is approximately big O of E, making it particularly efficient for dense graphs. Here's the code for the find and union functions. Topological sorting provides a way to detect cycles in directed graphs. Topological sorting is a linear ordering of vertices such that for every directed edge UE, vertex U comes before V in the ordering. This is only possible if the graph has no cycles, meaning it is a directed acyclic graph or DAG. Therefore, topological sort can be used to detect cycles in directed graphs. If a topological sort is not possible, then the graph has a cycle. This can be implemented using depth-first search or DFS with a stack. The time complexity is big O of V plus E. It is used in scheduling, build systems, and dependency resolution. possible topological sort is shown: 1 to 3 to 7 to 6 to 2 to 5 to 4 to 9 to 8. In summary, cycle detection is a fundamental graph algorithm with diverse applications. These applications include detecting deadlocks in operating systems, finding circular dependencies in software, circuit analysis for electronics, social network analysis, and compiler optimizations. Algorithm selection depends on the graph type. Use depth-first search or DFS, or union find for undirected graphs. Use depth-first search or DFS with recursion stack for directed graphs. Use Johnson's algorithm for finding all cycles in topological sort for checking directed acyclic graphs, or DAGs. Understanding cycle detection enables solving complex problems in computer science, systems design, and network analysis. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.